Solving radical equations in many ways is like solving any other equation that you've encountered before, except that there's one big difference, and we're going to introduce the concept of extraneous roots, which we haven't really seen before. And the reason why we get these extraneous roots is because if you look at the most basic radical equation, root A equal to B, you have to remember a few things about the way we define expressions involving the radical. The first one is that the A, which is the expression under the radical, we refer to that as the radicand. The radicand must be non-negative. So we know that A has to be greater than or equal to 0. Otherwise, we don't have a meaning for that. We can think of the square root of a negative number only if we include imaginary and complex numbers, which doesn't happen in high school curriculum. So the radicand must be greater than or equal to 0. And the other thing is the B value also has to be greater than or equal to 0, because even though every positive number has two square roots, for instance root 16 has the square roots of -4 and +4, when we use a radical we're only defining it as the positive or principal square root. So the B value, the right hand side of this equation, also has to be greater than or equal to 0. So we're going to see some of the equations are going to lead to reasonable looking roots. A root, recall, is just a solution to an equation. But it's always a good idea with radical equations to check and to see if what you have claimed is true really makes sense. And I'll give you a couple of very, very simple examples just to show you what can go wrong. If you have a very straightforward radical equation like root x equal to 3, the step that we're going to take to solve this is to square both sides. Now, when you're dealing with linear equations, you learned that as long as you do the same thing to both sides of the equation, it's fine. And you can add the same thing to both sides of the equation, subtract the same thing from both sides of the equation, multiply, divide, etc., and it's no problem. It maintains the inequality. Well, here we're squaring both sides of the equation, and for some equations this leads to perfectly reasonable solutions. So here we square root x and we get x, we square 3, we get 9, and let's check this by plugging the root 9 back into the original equation. So instead of root x we write root 9 equal to 3, and that's fine because root 9 is 3. So this is no problem. But let's see what happens with a very slightly different radical equation. What if we have root x equal to -5? So we take the same first step. We square both sides of this, and we end up with x equal to 25. Well, it looks reasonable, but when we go to check it, what we find is we're trying to claim that root 25 is equal to -5. And so you end up with 5 equal to -5, which is obviously wrong. So we call this 25 an extraneous root. It's a root of the equation, but we can't really claim that this is a true solution to the equation because when we plug it in we get a nonsensical statement. So it's an extraneous root. Now, one of the problems here, or probably the biggest problem, is that we're not really doing the same thing to both sides of the equation. When you square both sides of the equation, what is it you're actually doing on the left-hand side of the equation? On the left-hand side of the equation, you're multiplying root x by root x. On the right-hand side of the equation, you're multiplying -5 by -5. So you're starting off with this assumption that root x is equal to -5. And if that's not true, if there is no value of x that makes root x equal to -5, then you're not really multiplying both sides of the equation by the same thing. And that's why we end up with what looks like a reasonable solution, but it isn't. So I would suggest that you always check, and when you get into more complicated radical equations a little bit later on in the book, not in this chapter, you may have two roots, and you may find that one root is fine, the other root is extraneous, or you may find that both roots are extraneous. It's just always a very good idea to plug in your answers and check to see if they make any sense. So I'm going to give you a more complicated example here, but I'm going to start with an equation that doesn't have any radicals in it, just to remind you what to do with such an equation. If you had a straightforward linear equation like 3x plus 5 equals 11, you'd want to isolate the x term first by subtracting 5 from both sides, and then you could isolate x by dividing both sides by 3, and you get x equal to 2. Well, we're going to do exactly the same steps if we have a radical equation like 3 root x plus 5 equals 11. So we will subtract 5 from both sides here and divide both sides by 3. And then we can proceed with the step of squaring both sides. So if you square root x, you get x. If you square 2, you get 4. And even though you probably don't need to plug this in to check it to make sure it's valid, with experience you won't need to check it, but at the beginning always check it. 3 root 4, right? If x is equal to 4, we have 3 root 4 plus 5 equals 11. The left-hand side becomes 3 times 2 plus 5 equals 11, which is 6 plus 5 equals 11, which is true. So that's fine. X equals 4 is a valid root. What if you have two radicals? So let's say we have 5 plus 3 root x equal to 6 root x minus 10. Well, here the radicals have the same radicand, x, and so we can collect these in much the same way we would collect the x terms if it were 5 plus 3x equal to 6x minus 10. I like to collect the variables, or in this case the radicals, on the side that gives me a positive coefficient. So I'm going to subtract 3x from both sides. That'll leave me with 5 on the left. When I subtract 3x from 6x, I'm going to have 3x on the right. And now I'd like to isolate that 3x. I'll add 10 to both sides. And finally I'll isolate the root x by dividing both sides by 3. And now I can take the step of squaring both sides, and I get x equal to 25. Let's plug it in to see if that makes sense. 5 plus 3 root 25 is our left-hand side. 6 root 25 minus 10 is our right-hand side. So this is 5 plus 3 times 5 equal to 6 times 5 minus 10. So this is 5 plus 15. This is 6 times 5, which is 30, minus 10. And you can see on both sides you get 20. So 20 equals 20. No problems whatsoever. All right, what if the two radicands are different? What can we do? Well, let's take an example here, like x plus 12 on one side is a radicand, and the other side, let's say we had 3, x plus 20, so we have root 3x plus 20. So we can't collect the terms, but we can square both sides. If we square both sides, we get x plus 12 equal to 3x plus 20. And this is now a straightforward linear equation. I can subtract x from both sides and get 12 equal to 2x plus 20. I can subtract 20 from both sides, and then I can divide both sides by 2, and I get x equal to negative 4. Now the fact that I have a negative value of x is not a problem in and of itself, because x is not the radicand. So when you go to check this, you're looking for a couple of things, and one of the things you're looking for is to make sure that the radicand is not negative. Well, when you plug in a value of negative 4, you get negative 4 plus 12 as a radicand on the left. On the right hand side you get 3 times negative 4 plus 20. So this becomes root positive 8. On the right hand side you also have root of positive 8, and so that's fine. Let's do another one though. What if we have root of 5x plus 7 and root of 3x plus 1. So now if I square both sides, I get 5x plus 7 equal to 3x plus 1. I'll subtract 3x from both sides. I'll subtract 7 from both sides, and I get x equal to negative 3, not negative 2, negative 3. So let's take a look at the double check now. When I plug in the negative 3, I have root of 5 times negative 3 plus 7 on the left-hand side. On the right-hand side, I have 3 times negative 3 plus 1 as my radicand. So this is negative 15 plus 7, and this is negative 9 plus 1. So this is the square root of negative 8 and the square root of negative 8. Now, you might look at that and say, well, I might not be able to calculate the square root of negative 8, but surely the square root of negative 8 is equal to the square root of negative 8. And that argument holds water if you allow for the existence of the square root of negative 8. And again, later on in math, you will say it's all right to take the square root of negative numbers. The square root of negative 1, we can just make up a number. We'll call it I, the imaginary unit, and then you open up a whole branch of mathematics from there. But in the high school curriculum, we limit ourselves to real numbers, and we insist that the radical must have a positive radicand. And if it doesn't, then we don't assign any meaning to it. And you cannot say that something which is undefined is equal to something else which is undefined, which means that this negative 3 is an extraneous root, and this equation has no roots. So there are simply no solutions. All right, and again, that's a little bit difficult to get a handle on, and you come up with a different answer a little later on in math once you allow for the square root of a negative number. But for now, we just say that there are no real roots here. There are no numbers that make the left-hand side equal to the right-hand side. And you stop there. Now, later on, we're going to get into more complicated radical equations, which lead to quadratic equations. But we have to look at quadratic equations first, and that comes in chapters 3 and 4.